Hello, everybody. Selman here. Welcome to another edition of Physics 150 discussions on YouTube. And so, an earlier iteration of this problem did not make the cut on YouTube for whatever reason. I think I've got to cut a shorter video. I'm going to try and make these under 20 minutes. Again, if you've got any suggestions, please leave a comment on YouTube or send me an email. So let's get started. And so the format that I have here is obviously I'm screen sharing from an iPad. And the first step I'm going to do when doing any of these problems is redraw the diagram if it's given, because I can't edit this directly the way that I have this set up. So let's just draw this. And make sure to draw a nice big picture. So there's here, this is the first resistor. Make sure we draw the battery in the correct orientation as shown. And we've got a resistor on the top. I'll label these as we go. There's another one here. Make sure to label this battery also in the orientation shown in the diagram. Okay, so let's call this R1. This is R2, R3, R4, and R5. Let's call this one V1, and this battery V2. Okay, very good. So let's sort of just read off what we're going to be looking for. For part A, we want to find the voltage across each of the resistors. So I'm just sort of going to lay out how I anticipate working this problem out. And that's the following. It's a good idea anytime you're doing something like this to just write out the equation that you would want to know to solve whatever it is you're trying to solve for. And so in this case, it would be good if I could solve for the voltage drop across each resistor. I'm going to label I for an arbitrary resistor 1 through 5. And I could solve for that if I knew the current going through that resistor and the value of that resistor. So going back up, what we see here is that we've got a single loop problem. What that means is that when there's a single loop, there's the same current going through the entire loop. It's the same value of I throughout the entire thing, because this is just one big circuit in series. So the current is the same through every component. So that's important so that when I go back down to solving this equation, I know that the voltage drop across each resistor is the value of that current, because it's the same through every single resistor now because they're all in series, and times the value of the resistance of that resistor. Now, of course, we have that value. That's given as part of the problem. For example, R1 is 10 kilo ohms, as is R3, as is R4, as is R5 as well. The only one that's different is R2, which is double that, and it is 20 kilo ohms. So as you can see here, we could solve for the voltage drop across each resistor if only we knew the current. So what we're going to go ahead and do is use Kirchhoff's rules to compute the value of that current, and then we're going to plug that value back in for each of the resistors. Okay? Seems like a good deal. So if you remember, let me just go down here and write what Kirchhoff's rule, one of his rules, named after Gustav Kirchhoff, and that is that, so Kirchhoff's rule, so this is one of them, and that is that the sum of the potential drops around a loop have to equal to 0. Very good. So when we go back to our picture, what that means is that I have one loop here. You pick an orientation for the current, And then you consider how the voltage drops across each of the components. So the way I'm going to do this is I'm going to start from V1. That's just convention. As for myself, I mean, that's not a standard convention. You just pick a spot to start on, one of the batteries, and you say, okay, now if the current is going in this direction, then V1 is going to have a positive potential difference because going from the negative to the positive is in the same direction as the current. So that one's going to be positive, and then you're going to have a voltage drop, meaning you're going to get a negative value across the first resistor, negative I times R1, negative I times R2, so on and so forth. The second battery, because it's aligned opposite to the direction of the current as we've labeled it, that's going to come in with a negative sign, okay? And then for R4 and R5, you're also going to get negative signs. So let's just go back and let's implement this Kirchhoff's rule in practice. So for us, what we're going to have is V1 minus I times R1 minus I times R2 minus I times R3 minus V2, remember, because that battery is opposite to the direction of the current, minus I times R4 and minus I times R5, and that's all equal to 0. Now we're going to solve this for I. Okay, that's our goal right now, so let's just give ourselves some space. Okay, so the way that we're going to solve for I is we notice that I is common to all those terms with the resistors multiplied to them. So I'm going to bring all of those terms to the right-hand side of this equation by adding by all of those terms. So what you're going to have left over on the left-hand side is V1 minus V2, and that's going to be equal to, the current is going to be a common factor, times R1 plus R2 plus R3 plus R4, and altogether there's 5 of them. Now, it's important to, even though this looks like a sort of daunting task to solve for I, remember that whatever is in the parentheses is actually known. R1 is 10 kiloohms, R2 is 20 kiloohms, so on and so forth. You can just add those numbers up. So this is just I times some number that we already know. On the left-hand side, those are also numbers that we know. In fact, I didn't write them, but in the original problem, text, what we saw was that V1 is 12 volts and V2 is 24 volts. So we know both of those parameters as well. So what I can do to solve for I is just divide by this, by whatever's in the parentheses, that big hulking mass of stuff, because that's just some number. So what you get from that is that I is equal to V1 minus V2, whatever was on the left-hand side there, divided by the sum of all those resistors, which I'm going to write in a compact form like this. Now, let's actually go ahead and see what that is. That's 12 volts minus 24 volts. Very good. And then we're going to divide by the sum. So R1 was 10 ohms, and the rest of them were all 10 ohms except for R2. So that's 40 kiloohms. Sorry, I said ohms before. And R2 is 20, so that's going to be 60 kiloohms. Very good. So now you're going to have to take out your calculator and make sure you do that so that you make sure that we're not making a mistake either. And the result of that one is going to be 2 times 10 to the minus 4 amps. Let me just write this down. Sorry, and that number is going to be, the negative sign is to show that we picked the incorrect orientation for the current. Originally, we just labeled the current as going in that direction. We didn't give any reason for it. We just said, okay, if it was this, then this would happen. When you get a negative number, it just means you picked the incorrect orientation. That's fine. So you get minus 12 volts divided by 60 kiloohms, and this is going to be minus 2 times 10 to the minus 4 amps. Now, of course, as we mentioned before, the reason that this is important is because I could now solve for the potential drop across each resistor, because now I know the current I, and I also know the resistance for each resistor. So let's go ahead and compute those things. So the potential drop across the first resistor is the value of the current times the value of the first resistor. So this is 2 times 10 to the minus 4 amps times R1, which is 10 kilo ohms. This is going to give us looks like 2. So this is going to be equal to 2 volts. Now, of course, because resistors 3, 4, and 5 are also the same as this is going to be the same as the potential drop of 3, same as the potential drop of 4, and of 5. The potential drop across the second resistor, well, the resistance is going to change by a factor of 2. So we're going to see that the potential drop just doubles in this case. So this is going to be 4 volts. Okay, so that's part A. Now part B, let's go up and remember what this looked like. Part B says, what is the total power supplied to the circuit by any of the batteries that are spending energy? Now, in this case, the case of a single loop circuit, it's kind of easy to see which of the batteries are spending energy because it's just the voltage that's biggest. There's two batteries. They're both going in opposite directions as far as how their positive nodes are aligned relative to a current. And in this case, what's going to happen is that it's going to be the 24-volt battery that's actually spending the energy, and then the other one is going to be storing the energy, or storing the power. I'm sorry, I misspoke. So actually, the answer to part D will concern the first battery, V1. The answer to part B is going to concern the second battery, V2. So Jesse, in his PDF solutions, sort of solved for those two things together. Everything on those solutions is completely correct and complete. He just solves them in a manner that's kind of distinct from the way that the problems are asked. But part B, the energy stored or the energy supplied by the battery, I keep saying energy. The power supplied by the battery is going to be the power is equal to the current times the potential of that battery. So for the second battery, which is the larger one, you have that this is the current that's flowing through it times the potential of the second battery. This is 2 times 10 to the minus 4 amps times 24 volts. When you compute this out, you get that this is 4.8 times 10 to the minus 3 watts. Okay, so what's important to note, and we'll touch on this later, is that this is the total power that is being spent in our circuit. And so the part C and D, in part C, what is the total power dissipated? In part D, what is the total power stored by the other battery? These need to add up to 4.8 times 10 to the minus 3rd watts, okay? That because the total power spent is by that battery, therefore it is consumed by the other components. So let's go to part C. What is the total power dissipated by the other resistors? So these are essentially, this is the power consumed by each resistor. So let's write that down. This is part C. And so the power consumed by a particular resistor is going to be the current going through that resistor squared times the value of that resistor. So we know that for, let's see, the first resistor, we're going to have 2 times 10 to the minus 4 amps squared times 10 kiloohms. And when you do that out, what you're going to find is that these resistors are using 4 times 10 to the minus 3 watts. Now, this is also going to be true for the other resistors that have the same value. So that's P3, that's P4, and that's P5. P2, because it's got a different value for the resistance, is going to be double that. So it's going to be 8 times 10 to the minus 3 watts. Very good. And so actually, if you find the total power dissipated by all of these, so this is power dissipated is going to be equal to the sum of the power dissipated by each of those resistors, then you're going to find that this is going to sum up to, well, you've got 4 copies of 4 times 10 to the minus 3 watts. That's going to be 16 times 10 to the minus 3 watts. Yes. Is it possible that I had some of these? Yes. Okay. So what it looks like here is that I had the exponent wrong on these. So this is not 3, but this is, if you can see what I'm doing, I'm actually changing the exponent on P1 to 4 times 10 to the minus 4. Times 10 to the minus 4. Okay, that makes more sense. So that when we sum all these up, you're going to have 4 copies of 4 times 10 to the minus 4. That's 16 times 10 to the minus 4, plus 8 times 10 to the minus 4. All that adds up to 2.4 times 10 to the minus 3 watts. Now, the last problem, part D, what that asks for is the energy that's stored by the other battery. And if we want to find the energy that's stored by that battery, I'm going to use V1 subscript to make this obvious. Then this is going to be the current going through that battery times the potential of that battery. And when you compute this out, this is 2.4 times 10 to the minus 3 watts. Now, when you add those two things together, you find that 2.4 plus 2.4 is 4.8 times 10 to the minus 3, which is, if you notice, exactly the number that I have right here from part B. So those two numbers add up, which is a sanity check on what we did. Okay, so if you have any questions, send me an email or maybe post a comment on the YouTube channel. Okay, thank you very much. I'll see you around.